Welcome to our today's webinar on how to write secure Ethereum smart contracts. Happy to have you all on here. My name is Kevin. I'm responsible for partnerships at ChainSecurity, and I'm your moderator today. Let me briefly introduce you to the company ChainSecurity and today's presenter. ChainSecurity is a blockchain security company based in Switzerland and was founded in 2017 as a spin-off from ETH Zurich's IC Center, which is one of the leading blockchain security research labs in the world. The company is specialized in smart contract auditing and has established itself as one of the top auditors on Ethereum and Silica. The company developed a set of tools such as vulnerability scanner Securify, the formal verification tool called VerX. The company's track record is about 100 smart contract security audits for clients in more than 20 different countries. Such projects include Kyber Network, Paxos, the stablecoin Augur, and many other startups, regulated financial institutions, and licensed banks. Maybe you know the company from an incident earlier this year, which happened in January around the Constantinople upgrade delay, where an issue was found in EIP 1283. And very happy that today's presenter, Hubert Ritzdorf, was the one leading the efforts in discovering the vulnerability in EIP 1283 and is the co-founder and CTO of ChainSecurity. Brief introduction who Hubert is. Besides finding this vulnerability, he earned a PhD from ETH Zurich. He worked on security of cloud and blockchain services for more than 5 years. During his research, he analyzed existing and proposed novel protocols. As part of his work as ChainSecurity, he audited more than 50 blockchain projects. And today, Hubert will give you an overview of the end-to-end process of developing secure smart contracts in Ethereum, which will be followed by a Q&A.
Yeah, hi everyone. Very excited to be here. Thanks so much for the introduction, Kevin. So yeah, we are very excited to finally start the ChainSecurity webinar. It's something we've been planning for a while and got quite some demand for. And today we will start with what we work on most frequently and therefore probably know best, and that's how to write secure Ethereum smart contracts. So the problem with Ethereum is well known, namely not only Ethereum, but also other kinds, namely there has been plenty of hacks. Of course, not all of these hacks have been related to smart contract security, but smart contract security is a central component of that. So what we want to do as part of this webinar, and also today, I will briefly introduce what it is about. So the webinar overall is called Secure Smart Contract Development. And today in particular, we're going to talk about secure Ethereum development. So what are we going to talk about when it comes to Ethereum development? Today, the idea is, given that it's the first one, we would like to give you a little bit of an overview. So we will talk a little bit about preparation and specification of writing smart contracts, some good coding practices, common mistakes, security testing, formal verification, and code audits. As you have already realized, these are quite a few topics, so we cannot go into all of them in full detail today, given that we have limited time. So our idea is that we give you an overview today, and then after today, you can pick what you found most interesting. Because at the end of the presentation, first of all, there's going to be a Q&A session where you can ask questions. These questions you can already ask while the presentation is going on in Zoom's Q&A tab. And then at the end of the presentation, when you leave, you will automatically receive a feedback form. And in this feedback form, not only can you give us a little bit of feedback on today's event, which would be great, but also you can say what you would like to hear about next. So which would be even better, because we really want to tailor this to what people are most interested in. So yeah, this is gonna pop up for you automatically as you are gonna leave the Zoom call at the end. So now finally, let's get into it. So when we want to do smart contract development, it starts with preparation and specification, and that's where we see that a few common mistakes are being made. So we wanted to point a few of them out. So typically the first question is which blockchain to pick, and today we're as I said, we're only going to focus on Ethereum, so this is an easy choice for us today. But then there are a number of project considerations, and typically what we see, what is not considered sufficiently enough, is what roles need to be considered in the system. So what kind of users exist, and then how much decentralization can we achieve, because after all, that's what using blockchains and using Ethereum is about achieving decentralization. So if we have this concrete example, we have a contract. What we often see, or very commonly see, is that this contract has an owner. This doesn't have to be inherently a bad thing, but this owner is typically a more privileged role for this contract, which, first of all, that's absolutely needed, right? Because we have to define our access control. By default, everyone can access all the functions. So we need to introduce some roles. But this owner, the question is, how much power should he have? How much power does he have? And often we see that the owner has total power over the contract, which kind of defeats the idea of decentralization. So what can be done instead is power can be delegated among multiple people. There can be maybe an owner, there can be admins which have less privileges, so that we can keep the security principle of least privilege. Or we can try to remove the single point of failure we have with the owner, and, for example, replace it with a multi-signature system where even if a single key gets stolen, not the contract's security is not compromised. Another common example is that when we have different roles, such as a buyer and a seller in an exchange contract, people do not clearly specify what the interaction should be like. So, for example, what kind of influence should the seller have on the buyer's transactions? A common, this goes into the topic of front running and so on, where the seller might be able to trick the buyer into paying a higher price than he originally wanted. So these kind of problems. So for all of this, we need to clearly define what are the roles, how are they interacting, and what is the combination there. And then finally, given that our smart contract doesn't typically just exist in a void, but we want to include it into a bigger application, we need to decide what part of the code is inside the smart contract and what part is outside in the dApp. And inside the smart contract, in a way, we want as little as possible, but as much as necessary, because as we are well aware, executing inside the smart contract is relatively expensive, right? So you might have to pay, like if you're doing a really expensive operation and the gas price is high at the moment, you might even have to pay $1 to run your Ethereum transaction. And then the last important step is that we think about trust assumptions. So, for example, we had the example before of having an owner, an admin, and so on. Whom do we trust? And to which degree do we trust them? Do we think they might make a mistake? Do we think they might make a typo? Do we want to account for that? Like, do we want to make sure that we can correct a typo, that we can correct an accidental mistake? This is very important, and this is something that often only comes up at the end when it's hard to change them. So, as an example, admins are often fully trusted. So if they make a typo, then so be it, and then the contract security then the contract might be broken afterwards. But that's of course not the optimal situation. And then finally, in terms of users, we have the common KYC AML requirements on the users. What's also commonly an issue which we see as auditors is the timeline. So of course, you will have to evaluate how much development and testing time you need. And then finally, of course, we would recommend that you get an audit. But for that, you need to plan your whole timeline, because in the end, after the audit, it's likely that you will have to make extra changes. You might have to make some adjustments. And in order to get all of this done, you should have a proper timeline. Especially true if you have complicated integration tests. So depending on what your smart contracts are interacting with, testing becomes more complicated, and you want to retest after significant changes. So this is then a bigger undertaking. Finally, when it comes to preparation and specification, in some situations, we have to think about how critical gas optimizations are. So for example, if we're deploying a custom smart contract for every user that we're onboarding, then we want to obviously keep the cost for this operation as low as possible. And while we're developing, we also need to think about how we can test most efficiently. And often that's using, for example, a test chain deployment, because there we already face a lot of the real world problems that we will face later. And one very big problem that we could talk about for hours is the management of private keys that we will also go into eventually. Something we just want to point out, because it might not be obvious to everyone, is you also have to, even if you already decided on Ethereum, you have to pick a programming language. Obviously, this Solidity is the super dominant language at the moment, but there's many other things you could do. Viper gained some popularity recently as the Uniswap exchange is implemented in Viper, but we would generally advise to stick with Solidity, as tool support is best around Solidity. So that brings us to some coding practices. So what should you do? What should you not do? What kind of things should you maybe look out for? Well, a lot of these are just common coding practices that we see whenever we have to handle unsanitized input. And so be it web or any other network programming. And same here, we want to validate inputs and outputs. But what's then specific is, for example, gas costs. So with gas costs, you can optimize for, generally you want to optimize overall to make sure that the gas costs are as low as possible. But you can sometimes trade off a little bit between deployment and use gas costs. So gas costs that have to be paid every time the contract is being called, versus gas costs that only have to be called once. So that depends a little bit on how frequently you expect to call the contract, how you make this. And then one big topic which we will discuss now in more detail is going to be upgradability. Then common problems that we will also get to a little bit later are when calling and delegate calling. And this one is about pull or push payment. So what we refer to here is that smart contracts can send you money actively, or they can allow you to withdraw money. And so when they actively send you money, it's called a push payment, whereas it's called a pull payment when they allow you to withdraw money. While this is, the usability is of course better if it's a push payment, as in you just receive it and you don't have to do anything. Pull payments are generally favorable in terms of security, because on Ethereum, payments can fail, and hence a failed payment can block progress in your smart contract, or can potentially deadlock your smart contract. So this is something that you generally want to look out for. Finally, we always recommend to use well-known libraries. No need to reinvent the wheel. The common ones here are, of course, OpenZeppelin or something like the Gnosis Multisig Safe. Yes, that have been audited and looked at many times. And then we have, this is a common one, which is called the check effects interactions pattern, which just tells you how to structure your code so that you are less likely to make mistakes and more likely to spot something missing. So where you write all the checks in the beginning of your function, the effects are then being triggered. So for example, writes to storage later, and finally you do perform the interaction, so you call other contracts. Obviously that's not always so easy to do, but whenever you can do it, it really makes it easy to see whether the code is correct or not. And the consensus has collected a very good list of best practices that we generally recommend. And as I said, we're going to talk a little bit in more detail about upgradability today, to give you a little teaser of what good practices can be. Yes. So upgrading Ethereum smart contracts. So you now might be, wait, I thought the whole point of smart contracts were that they cannot be upgraded. Well, that's correct, as in the sense that smart contracts are immutable, but there are still ways how we can upgrade them. So the first way is when we use migration. So here, this is something that is the, let's say, preferable option from a lot of people's perspective in terms of security. So what do we do in migration? We ask the user to agree that we want to move to a new contract. So it's a bit like when a company asks you that the general conditions have changed to acknowledge the new one. And here we have full flexibility in terms of what to transfer to. So how it works is the user typically triggers the new implementation or the old implementation, depending on how this works, and one of the two. And then they, for example, the new implementation would load the state from the original implementation. And for example, if this would be a token contract and the user had 100 tokens in the original token contract, the new implementation would recognize that originally 100 tokens belong to this user. So now through the migration process, the new implementation would also make sure that the user is given 100 tokens. So this is relatively easy. It requires us to offer certain interfaces for the original implementation, but these are typically anyway available. However, there's often now another technique being used, and that's the transparent upgrade through a so-called proxy pattern, which is technically more complicated. And there are also different ways how this proxy pattern can be implemented, where, as I said, we unfortunately don't have too much time to discuss all the details. So let us know if, for example, this would be something that you would be interested in. And this, as I said, is a bit more tricky because it can break the trustlessness that we want to provide with smart contracts. So that's why this trade-off needs to be carefully evaluated. So how does the second option work? So in the second option, whenever the user calls a smart contract, he in reality calls a proxy contract. And for example, this proxy contract simply has a variable where it stores the address of the actual implementation. And while you cannot update code, you can update the state of smart contracts, right? So you simply change this variable, and instead of calling the original implementation, now whenever the user calls the proxy, it is being forwarded to the new implementation. So the benefit here is that it's transparent for the user, but that's also the disadvantage, because the user has no way to do something about it. And in a way, the user never knows what kind of code is going to be executed when it calls the smart contract, which defeats the purpose of the smart contract a little bit, as the idea of the smart contract is that we kind of know what's going to happen. So yeah, this was just a brief example of things we have to look out for in coding practices, and leading us now to common mistakes, where again there's a great list already in the smart contract weakness classification. So we're not going to go through all of them, but we're going to point out some of them in the following slides, namely missing authorization. So let's get into that. So you might have heard of this. So this is a case study of the Parity multi-signature wallet. So bug number one is what technically we call this an unprivileged right to storage. So as I said, whenever we have a smart contract, we need to make sure that it has proper authorization in place, so proper access control basically. And a multi-signature wallet, what it does is it's a contract that's jointly managed by different users, and it lets different users make decisions together. So this is something that you might know from the corporate world. When there's an important decision, multiple directors have to sign it. So here, by signing, we mean cryptographic signatures. And this is something that's really easy to do on top of Ethereum, which otherwise, if you have tried to do this, it's typically quite hard to do. Because Ethereum already does all the key management, all the signature verification for us, because every Ethereum transaction is already signed. So we can kind of just recognize what the different people want and count this in a multi-signature wallet. So, but this is just about general what multi-signature wallets are. So let's look at this particular multi-signature wallet. So here we have a withdraw function where we are doing a proper access control check. Namely, we're checking if someone is an owner here, and if that person is an owner, then we're allowing this transfer to happen. And the transfer is transferring Ether away out of the contract. So this withdraw function is actually correctly implemented. However, unfortunately, there was this other function, this init wallet function, which was only supposed to be used during initialization, but was kind of forgotten about. And it allowed anyone to reset the owner. So what happened was the attacker in the first step, made himself the owner, and then in the second step, called the withdraw function, which was now legitimate because the attacker was now the owner. This was used to steal roughly 150,000 Ether, so at peak time, roughly $150 million in July 2017. So a quite significant bug. Of course, this bug is a little bit oversimplified here. The whole contract is a little larger. It's slightly more complicated, but this is in the end what it comes down to, that it was possible for anyone to reset the owner and thereby circumvent the access control check. The second bug we're going to look at here, which is kind of also a common mistake, is the reliance on other contracts, so the dependence on other contracts. So again, it's about the multi-signature wallet. So the multi-signature wallet was implemented in such a way at the time that there was a main contract and there was a library contract. So you might have heard of library contracts, but you might have not, because they're not very common. So the idea with library contract is that you can delegate certain calls to the library contract, where basically the library contract is a central place where certain pieces of code are stored that are then invoked as you would know it from a traditional library. So this is working quite well. And why are we doing this? Well, this allows us to execute the code from the library. So why are we doing this? Because we might want to deploy many wallet contracts, and they can then all use the same library contract. So the wallet contracts can all be smaller in size, which allows us to reduce the overall code size and thereby the overall deployment costs of the smart contracts that are being used here. However, the problem was that unfortunately, this library contract that was going to be used by everyone was not properly protected. So there was this famous GitHub message where this anonymous user said, oops, I accidentally killed it. And now that the wallet library was gone, it had been killed or deleted off, the code had been deleted, all these calls were going into nirvana, so nothing was happening there anymore. So basically, the complete functionality of these wallet contracts was gone. So because the functionality was gone, they were now all in a deadlock state. So all of these contracts are still on chain, of course, and they still hold lots of money, but this money is now frozen due to this accident. And here again, we're talking roughly $100 million. So finally, in terms of common mistakes, a more technical example. So this might be obvious to some people, but I'm just going to give like a super brief excursion into numerical precision. So which is super simplified. As you might know, computers store numbers with limited precision. They don't have unlimited space, so they need to pick limited precision. And therefore, there's a maximum number. And for example, if we have 1 byte to store and we're storing unsigned, then our maximum number is 255 that we can store. So if we count up and we reach 255, we'll continue from 0. Hence, 254 plus 2 is 0, plus 3 is 1, and so on. This is what's being called an arithmetic overflow. So this was used in a contract. So here we see the contract to create free tokens. So you can check if you can spot the problem. So there was a regular transfer function, as you know it from all the ERC20 contracts, and this one is actually protected with a proper if, where we're checking that the balances of the sender are sufficiently large. And then there was a batch transfer function. And here we are doing multiple transfers at the same time, which can be quite convenient because we can do this in a single transaction. So, and here we can do it in a way that we send the same amount to different users. So maybe some of you already spotted the problem. While again, we have a proper check. So what are we doing here? So first, this total amount is being calculated, which is the amount that we want to send to every user times the amount of users we want to send it to. So this actually sounds pretty good. So we're computing the total amount that we want to send around. And then we're checking that the balance of the sender is larger than this total amount. So this is, again, this is a proper check. Then we're subtracting this this balance from the sender, and we are adding it to the balances of all the receivers. So this all looks really good. So this was actually implemented in multiple contracts. And on the right-hand side, we see the state of the token contract at the beginning of the tag. The sender has 20 tokens, and we have 2 other addresses, A and B, which both have 0 tokens. And now, so the sender is the attacker. And now what the attacker does, it creates a new batch transfer where to 2 destinations, A and B, and the amount that it wants to send to both of them is 130. So what happens now? In this calculation of the total amount, we're calculating 130 times 2 because we're sending to 2 addresses. So 130 times 2, as we said, is not 260, but instead is 4 because of the arithmetic overflow. So now in the subsequent line, we are going to check if the sender has at least 4 tokens. And yes, the sender does have 4 tokens because the sender has 20 tokens. So the transaction will go through, and after the transaction, we're going to have this state where now the sender has like 16 tokens, but 2 other addresses that the sender controls now have 130 tokens. So we basically started creating tokens out of thin air. And in reality, the numbers are a little bit larger, as you can see. So this is a real world example where this happened. You can see someone created lots and lots of tokens for this for these 2 addresses, which are way too large. It could be displayed here properly by Etherscan. So this was part of a real attack that was performed against multiple token contracts. So that brings us to testing. So you should do proper testing. So first of all, Captain Obvious, checking in, smart contracts need proper testing. And your test cases should have high coverage. Luckily, as is the case in other languages, test coverage can be automatically measured. That can then look something like this, where you make sure that you're covering enough of the branches and the statements and so on. And it's really important when it comes to smart contracts to properly test the failure cases, because we often see test cases missing there, and people just assume that the transaction will fail, but it doesn't really fail. And finally, one thing that's being tested very rarely are the events. But what we talked about earlier is your smart contract is not just existing in void. So the events are typically triggering some off-chain computation or event or some change in the UI or something. And if these are not correct, then basically your overall application can break down. So we definitely recommend to also test those properly. Linters can definitely help because they also find some of the common mistakes. And lastly, there are security scanners, one of which we're going to look at now. And the one we're going to look at now is called Securify. Why are we looking at this one? Because we are most familiar with this one because we have developed it. Just to briefly give you an idea, so this is, you don't have to understand all of what's going on, but basically what Securify does is it takes the EVM binary, so you don't even have to, so you can run it on any contract that you see on the chain. You don't even have to have the Solidity code. And it generates some intermediate representation, then generates some mathematical facts, and finally gives you some results, some report. And it's fully automated, it's free. You can check it out on the securify.ch. And what you get is something like this, where here the red highlighted line has a number of issues that are then explained what they are. And if you click on info, you get more information. Securify is also open source, thanks to the Ethereum Foundation. And you can check it out on GitHub, fork it, contribute. Let us know if you have cool ideas. So, and then finally, while Securify can help us detect things like common mistakes. So you might have seen on the previous slide that it was highlighting things like reentrancies and so on. So it can help us to detect these common mistakes. This is not always sufficient. So like ideally what we would want is we want to not only know that we're not making any common mistakes, we want to know that our contract is behaving exactly correctly. And that's what formal verification can do for us. And here also in collaboration with ETH Zurich, by the way, the ETH has nothing to do with Ethereum. The university has existed for a little longer than Ethereum. There's some cutting edge research how to do this. So if we have a smart contract on the left side, where, for example, we have some of these variables, namely the deposit here and some function, and we have some condition that should be fulfilled. For example, the investor can claim refunds only if the sum of deposits never exceeded 10,000 ETH. So this is something you commonly see in a crowd sale. If the crowd sale didn't raise enough money, then all the investors should be able to get a refund. And that then can be translated into a formal property that's described here. Don't worry about the details, but basically we just want to show that it's possible. And then the contract and the property are passed into the VerX system, which then either says like this is verified, or tells us that it may not hold and gives us a reason why it may not hold. And why this is powerful is, in case it says verified, not only can it does it say like, okay, looks good to me, but it actually says there is an absence of any vulnerability. So like the problem with Securify and scanners like these is that we kind of have to be aware of the attacks to actively search for them, and we are searching for these common attacks. While here for VerX, we can really formally verify these properties. So no matter what attack you can think of, because the formal verification has basically tried all possible transactions out there, you can be sure that the code will work correctly. That leads us to the last point that we briefly want to discuss today in smart contract development, and that's audits. And audits is something we're quite familiar with, as this is what we're doing a lot of the time, as Kevin mentioned in the beginning. So here, what I already mentioned is that you should think about the time, as we often see people having to rush their audit. Then the audit typically starts with some initial kickoff where audit and developer kind of get to know each other and explain the process to, one explains the process, the other explains the code. Then we have the audit, which typically leads to the intermediate report, which is sent to the client for review and gives the client time to fix things. As I mentioned, so when you're doing an Ethereum project, remember that you have to allocate some time for these fixes, as you want to properly retest everything afterwards. Which these fixes are then reviewed by the audit company, which is very important, as we commonly see that these fixes are being made under a lot of time pressure, and therefore, while fixing one bug, a new bug is being introduced, which is very dangerous. So then these fixes are again reviewed, leading to a final audit report. So we just wanted to point out a few things to look for in an audit, and while doing that, also kind of explain a little bit how audits look at chain security. So as you would expect, we're using all the tools that I've already mentioned that we are well familiar with. We're also using fuzzing. Fuzzing, basically, you try with many different inputs, and this can be useful for certain properties that cannot be formally specified due to certain technical conditions. And finally, of course, we have a longer manual review where we also look into the things like game theory, which can sometimes be an issue, as we always have to assume that people are kind of driven by the incentives. We sometimes find that the contract's game theoretic assumptions don't necessarily hold up. Additionally, we are looking a lot into the trust assumptions. So as I mentioned, smart contracts should be as decentralized as possible, as trustless as possible, and we don't always see this. So we make recommendations how this can be improved, but we also point out to the users of the contract if what the contract does is different from what's being claimed. So sometimes you find claims on the website, something like all your funds are secure, no one can access them. But then in reality, in the contract, there's some function for the owner to withdraw any funds. That is then something we would raise here. And finally, we get the report as described. So just a quick sneak peek how such a report can look. These are also available online. So with security issues, we describe what the issue is, give like an example, and then also say what the client did to fix or address the issue. And then, as I mentioned, we also describe trust issues. Finally, as I said, this is only the introduction. So security never stops. This keeps going for a long time. There's many more problems. So I'm just teasing here now a little bit. as there will be many, many more topics that we would love to talk about as part of this webinar. And this brings me to the conclusion. I just want to say 2 quick words about chain security. So as already has been mentioned, we're doing audits on all kinds of either low-level blockchains or smart contracts, and additional consulting on top. And as also already has been mentioned, these tools are being developed in collaboration with ICE Center, which is an interdisciplinary research center at the Computer Science Department in ETH Zurich, which is one of the top universities in the world when it comes to computer science, where we are one of the startups. So this brings me to the closure of this presentation. Here we have a QR code that leads you to our monthly Ethereum security digest, where you also find a link to subscribe to that if you're interested in that, where we'll also notify you about all kinds of other things that we see and find interesting. And with that, I'm going to hand back to Kevin for Q&A.
Thank you very much, Hubert, for covering so many topics in such a short time. So the questions are slowly coming in, but let's get started. That we have maybe another 5 to 10 minutes to answer questions. If you have any further questions later on, we will send you some options that you can contact us and just send them over. So the first question is from Rohit. He asks, does VerX and Securify work with smart contracts written in chain code?
Yeah, that's a very good question. So VerX and Securify are Ethereum specific, but we also have a tool that works on chain code. So maybe not everyone's aware, but as we said in the beginning, there's many blockchains out there, and one of them is Hyperledger Fabric. So part of the Hyperledger framework, and Hyperledger Fabric, their smart contracts are called chain code and can, for example, be written in Golang. And if you go to chaincode.chainsecurity.com, you see that we also have a scanner for chain code, which works quite similarly to Securify. So it also finds kind of common mistakes.
Yes, another question from Andre. He asks, what is the most common mistake in terms of security in smart contracts?
Yeah, so the most common mistake is kind of the one that the first one we highlighted with the parity issue, which is kind of incomplete access control, I would say. So as we said, anyone can call any function on a smart contract. So you need to make sure that only the right people or only the right contract can call these functions. So this is typically where we see the most mistakes, because the problem is, as usual, security is about the weakest link. So even if in 99 functions you correctly check the sender and correctly check the authorization, if you just forget it in one of them, then the attacker can use this and exploit this. So I would say the most common mistake is like incomplete access control, so that you can call a function that you are not supposed to be able to call.
There's another question from Miguel. He asks about static and dynamic analysis, if it's a good idea to differentiate these parts or not, and what tools and techs ChainSecurity is using. Yeah,
again, a very good question. So yeah, I think it does make sense to differentiate them a little bit. So again, I mean, as usual, a combination of all the tools is most powerful, but there's certain things that you can find better with the one technique and certain you can find better with the other. So Securify, as I mentioned, is a static analysis tool, and Securify, I mean, you can it can run for a while, but you probably don't have to run it like after every commit necessarily, but you can run it, let's say, once a week or something, just to check that you didn't introduce something you totally didn't expect. Well, some of the dynamic tools, like, I mean, the most obvious case of dynamic testing is dynamic checking is just testing. So there, that can be done more frequently because it's just less time intensive on. But yeah, so it depends a little bit. Of course, as part of the dynamic testing, you can also do, or dynamic analysis more specifically, you can also do symbolic execution. And there's also really good tools out there for Ethereum. However, they take quite some time to set up. So really the benefit with Securify is you just paste in your code, you press analyze and it just runs. Whereas, for example, some of the dynamic analysis tools, they might require some additional setups.
There is a question from Vivek. He asks if the audit process will always include some manual review parts. That's
a very good question. So we anticipate that it will probably always include some manual review parts, simply because from our experience, specifications are typically not complete. So if we would receive an entirely complete specification, and if we would have perfect tools where we have perfect confidence, then we could say, okay, we don't need the manual review anymore. But often through the manual review, for example, we see a function that wasn't described in the specification. And if it's not described in the specification, then we wouldn't also find any bugs in it. So things like this that are just not, that we then uncover with manual review, and the other things that I already mentioned, so things like game theoretic analysis and so on, that are typically easier to do manually rather than having a tool that can think of all possible situations.
All right, there's another question from Casimir. He asks if he includes libraries like OpenZeppelin, which introduces more functions and roles than they actually need in their smart contract. What should they do with it? Is it just should they just delete it, or should they keep it?
Yeah, that's a very good question. So what we find is most elegant is that because it's the cleanest solution, you inherit from these functions and you use these functions. So typically in smart contract, in Ethereum, sorry, in Solidity, libraries are used through inheritance because Solidity has this complex inheritance scheme. And so you inherit from these functions, and then what you can do is you can override the functions that you don't need with kind of, for example, a simple revert statement that will then reduce your code size, but will also make sure that there is no additional attack surface that you didn't think about. And this kind of particular way allows you to include these libraries very cleanly, so you don't have to mess with the libraries, you don't have to copy paste library code around, you kind of just include it as a whole, and you delete the ones you don't need by overwriting them with reverts. So that's typically what we find most elegant.
Cool. Florian asked, what is the recommended Ethereum testnet?
Good question. So it depends probably a little bit what you're looking for. So in general, I would say Robson. So Robson is the official testnet. So this is when you're really doing kind of final stage testing, or you're doing a beta test with your users and so on, then I would say Robson, because that is gonna kind of realistically show you a lot of the problems that would also appear on the mainnet. You can also use Kovan if, for example, you think that like things like timing and so on are not relevant, because Kovan has faster block time. So maybe you're annoyed of waiting for Robson sometimes. But of course, if in early stages of the development, I would say the best testnet is your local testnet, where Ganache is still probably the best option, even though sometimes there's some minor diversions to the established clients. Ganache is typically the best option still there. So yeah, it depends a little bit which phase you're in, but that's, I guess, what I would say about that.
So a follow-up question here from the chat is, are there potential surprises when moving from a testnet to the mainnet?
Yeah, so as I mentioned, so if you are using Ganache locally, then there can be potential surprises. So these surprises can be, there have been a few cases in the past where Ganache didn't calculate gas exactly as it was calculated on the main chain. So you were all of a sudden paying more gas than you were expecting. To be fair to the Ganache project, which is doing great work, this has been largely eliminated. So I don't know of any such bug that is left, but of course it can always reappear. So I would say this can also happen in terms of like the UI and what you would expect, right? Because if you test the UI against your local testnet, you will see like very fast responses and everything will work nicely. Whereas if you run the UI against the Ethereum mainnet, then obviously you will have to wait a little bit. So it might be as simple as you're displaying some loading animation showing the user that something is actually happening, and he has to wait for the transaction to be mined. But yeah, this depends a little bit on your settings. So something I just want to point out quickly. So if you are worried about that, but you still want to use a local testnet, for example, because you don't want to disclose the smart contract code before you really launch, what you can do is, so Go Ethereum also has a development mode, which is relatively easy to use. There's like a very, very long command that will start Go Ethereum in this development mode. And then you are running on a proper client, which just has shorter block times. So if you're worried about gas costs and the like, then you can do this. And final comment on this, to avoid such kind of such bad surprises when moving to the mainnet, you should of course not use special Ganache options that let you do something that wouldn't work on the mainnet. So Ganache, for example, if you explicitly ask it to, it lets you deploy larger contracts than you would be able to on the mainnet, because on the mainnet there's simply a limit on the size. But Ganache lets you disable this limit. So obviously, if you're doing that, then you might be in for a bad surprise on the mainnet.
There was another question from the chat. Maybe we're gonna do two more. Do you still see a lot of reentrancy related bugs even after some of the bigger exploits that happened in the past?
Yeah, that's a good question. So reentrancy in total, I think, has gone down a lot. I mean, I think there's two main components to that. First of all, people are more aware due to the big bugs and the education that has happened. And secondly, the tools and the environments help you. So for example, Solidity has added these functions which make it easier for you to prevent reentrancy. And there's tools like Securify which let you find such reentrancies. However, while they are relatively rare, we still see them from time to time in audits, so they definitely still are out there.
All right, then I think we are closing right on time after an hour. So thank you all a lot for attending. Once you leave, there will be a link that leads you to our survey. So you'll be very happy if you would take the 1 minute to fill in the survey that we can improve our future webinars. And I'm putting in the chat some links where you will find the email address if you have any further questions, that you can contact us via contact@chainsecurity.com, or you can also schedule a call with us through Calendly, and also put a link to our new monthly Ethereum security digest, where you can also sign up. So where we will put together some curated content on Ethereum security. And yeah, that was it all from my side. Thank you all for being with us, and hope to see you again on future webinars.
Yeah, thanks for the great questions. I hope you enjoyed it, and have a great evening or great morning, depending wherever you are.